Gas laws, where algebra meets the invisible. In gas laws, we're looking at how gases behave, and we're going to quantify it. We're going to use equations to look at how gases behave when we change temperature, pressure, volume, and amount, and what that means for a gas. All right, so just an idea of some basic algebra you need to understand before we get into discussing this. So we would say that a direct relationship means that two variables move in the same direction and when one of them is changed. So when the outdoor temperature increases, ice cream sale increases. Right, now in a statistic mindset, and I need to say this, direct variation or direct relationship does not mean causality. In this case, there are definitely some cause going on, that when it's out, hot outside, people want something cold and refreshing, and there's some causality there. But it's like you can also say, hey, as outdoor temperature, as ice cream sales go up, violent crimes go up. That is a true relationship. However, there is no causality going on there. So we have to be cautious as scientists and as people who teach science to be careful that when we say that something has a relationship, that we're not implying causality unless there is causality. Now, with gas laws, thankfully, there is. That one causes the other, and we'll kind of look at why. But just wanted to kind of give that disclaimer in terms of when we talk about relationships. All right, the opposite of this is what we call an indirect or inverse relationship. It means they move in opposite directions. So when there's more distractions in a classroom, the amount of student learning decreases. And so that makes common sense. So that's an indirect relationship. So, all right, so with the gas laws, when I teach this, I give my kids the laws because I don't want them to, I give them the equations. But they got to know which one's which, and they got to know how to use them and kind of understand what they mean. But it's not one of those things I spend a whole lot of time trying to memorize, all these equations, because as you'll see, there's a lot of equations, lots of letters, and lots of numbers. All right, so first law, Boyle's law. This relates pressure and volume in an indirect relationship, meaning is one goes up, the other one goes down. We need to assume that temperature and amount are constant. So here's the logic behind this one. When a gas has more space to move around, it has fewer collisions, and therefore the pressure decreases. So if I increase the volume of a balloon without putting more air into it, and there are ways to do that, that means the pressure in the balloon has to be less. If I decrease the volume, if I take that balloon and I squeeze it and I push it, the pressure inside the balloon is going to begin to increase. And if I can push that balloon enough and hard enough, and I can push it from every direction the same, I can exert more and more, and I make that volume smaller and smaller until the pressure gets so high that it finally pops the balloon. That's what happens when you step on a balloon. You're decreasing its volume, which increases its pressure, causing it to pop. All right, the equation for this is P1V1 equals P2V2. So where 1 is your initial, where you're starting. And then 2 is where you're ending, or where you're stopping. All right, so what's your initial pressure? What's your initial volume? What's your final pressure? What's your final volume? All right, so when things are in an indirect relationship, they will be on the same side of the equation. All right, so 1 and 1 are going to be on the same side. We'll see the other way in a moment. So let's look at what that looks like. So when doing calculations, you need to make sure that your units are the same. So like you're not going to start with pascals for pressure and all of a sudden switch to atmospheres. If for some reason your pressures are in different units or your volumes are in different units, then you need to fix that by doing a conversion. I'm not going to give you any questions like that. I've seen it happen before in books, but people don't really do that, and it's kind of crazy. All right, so here's an example. If a volume of a weather balloon is 7.59 meters cubed at atmospheric pressure, 101 kilopascals, then what is the volume when it rises to where the pressure is 1.21 kilopascals? These are true numbers from weather balloons, by the way. So just like we did equations earlier with the heat, I want to use the same method. First, identify your variables. All right, so I've got volume. So I've got a 7.59 meters cubed, that's a volume. And then I've got two pressures. One's my initial and one's my final. So the 101's the initial, the 1.21's the final. So I've identified my variables. Like I said before, for me, I would be writing, above this, I'd write V1, P1, P2. I wouldn't necessarily write it like this on my paper, but that's how I would identify which variable is which. After you identify your variables, we need to then identify the equation. Right now we've only covered one, but when we have all of them, we have to figure out which equation to use. And in this case, I'm given the variables of pressure and volume. That means I need to use the pressure and volume equation, which is Boyle's. So P1V1 equals P2V2. So then insert your known variables. Insert the known initial pressure, your initial volume, and your final pressure. We're solving for the final volume. Unit-wise, once again, the units are going to match up. As long as you're consistent with your pressures, your volumes are going to have the same unit. So the units are going to be meters cubed in this case. So do your math and you get to 634 meters cubed, which is huge. That's a very, very large balloon by the time it gets to the upper atmosphere. And so that's an example of how to run through Boyle's law. Second law, Charles's law. You will see this written multiple ways. You will see S apostrophe and S apostrophe S. I have done my research. Grammar-wise, apparently, rules have changed since I was in school, and this is how it is supposed to be written. Also, along those lines, gases, plural, can be spelled with one S in the middle or two S's in the middle. Both of them are in the dictionary. Why, I don't know, but that's what it is. All right, so Charles's law. So Charles's law relates temperature and volume, and it says they're direct, meaning as I increase the temperature of a balloon, it's going to get bigger. If it gets cold, it's going to get smaller. And so what kind of it says, as gas is heated, the molecules are going to be moving faster. So as I increase that temperature, they're moving faster, and therefore they're moving faster, they're hitting the container harder, and that's going to make my balloon get bigger. Or if I take a balloon, think about it, if you've ever put a balloon outside when it's cold, like for a party or something, within an hour or two, it's all of a sudden starting to sink. Part of that's because its volumes decrease, increasing its density, which makes it sink. And so that's going on. A really good example to do here, if you've got a water bottle, a milk jug, something like that, fill it with hot water. Get your tap water going as hot as you can get it. Fill it with hot water, dump that hot water out, screw the lid on. So now you have hot gas. Now you have hot air because the water heated it up inside your container. Screw that top on and put it in the freezer. And you will wait about 30 minutes and you'll be able to come back and you'll see that the container has begun to get crushed. And the reason being is this relationship that you decrease the temperature, and all of a sudden the gas is cooling off. The molecules are now going slower, so they're not able to push on the container as much to maintain the pressure, and their pressure inside decreases, which causes the pressure outside to squish it into a smaller volume. All right, this is how you will normally see this written. Most books will give it to you in this fraction form. I'm a firm believer that if I can not do fractions, that's always better. So I write it this way, that they're on opposite sides, that the two initial conditions are on opposite sides, the two final conditions are on opposite sides. And that just, basically all I did was cross multiply this fraction. But the more we can get away from fractions and not have to use them, the less math mistakes get made. And that's my experience with it. All right. Big thing. So as we look at an example here, so we've got what's the new volume of a 3.785 liter compressible container, aka a gallon milk jug. That's cooled from 98 degrees Celsius down to -5. That's kind of the example we were just talking about. There's something super important here. The temperatures must be in Kelvin. Because think about it, if I did this equation let me show you. So we identify the variables. Now here's my initial volume, here's my initial temperature, here's final temperature. So V1, T1, and T2. If you don't convert those to Kelvin, when you use this -5 here, you're going to get a negative number over here, which is going to give you a negative volume. Think about it. Can you go to the grocery store and buy a negative gallon of milk? Can you have a negative volume? It's not possible. We don't have containers that measure negative volumes. And so that's one of the main reasons why we can't use negatives, but it also has to do with what's going on with gases, and the whole Kelvin scale does just significantly better job of doing what needs to be done here math-wise. So we have to do Kelvin. And if you'll remember, we haven't used Kelvin a whole lot, but Kelvin just means you add 273. So 98 plus 273, 371. -5 plus 273 is 268. That's how you convert from Celsius to Kelvin. It's a very easy conversion, doesn't require anything mathematically other than simply adding 273. But our temperatures have to be in Kelvin to avoid all the negative craziness and other issues. All right, so then we plug in and insert our known variables. We plug in T1, 371. Plug in our final temperature, 268. We plug in our initial volume. This is why I think it's essential that you write down the equation without anything in it first. Because I think with these, it's easy to forget which side's which one's 1, which one's 2. And it would be very easy to put this volume here. And so by writing the equation without any numbers in it first, it'll keep you from putting things in the wrong spots. And that's why I like to do it that way, because I want to make sure and alleviate as many mistakes as possible. Because I make careless mistakes when I go too fast. And so this slows me down and keeps me from making careless mistakes. So then simply solve for your variable, and we get that the volume is 2.73 liters. That we lose almost 25% of the volume by changing the temperature. Okay. This one will be in some of your books. It may not be in some of your other books. But this is relating temperature and pressure, Gay-Lussac's law. Just because of the word gay in it, students will giggle. But anywho. So Gay-Lussac's law is relating temperature and pressure. And we're assuming that the volume is constant. So unlike my milk jug example, with my milk jug example, the volume of that container could change. I put it in the freezer, and all of a sudden that container is going to get crushed. It's going to change because, relatively speaking, the pressure is staying the same. But let's say I had a steel container. That pressure doesn't change quite. The volume won't change so easily. What's going to happen is the pressure is going to change. And so same principle in terms of the higher the temperature, the faster the molecules are moving, the harder they're going to hit the surface, or opposite. If I cool down the temperature, the molecules are going to move slower, they're going to hit with less pressure, and so on. So similar idea with the equation. Instead of writing it as fractions, I write it this way. Just makes life simpler. All right, I'm not going to run through an example of this one because it works the exact same way as the other ones. Temperature has to be in Kelvin. Identify your variables, plug them into the equation after you write down which equation you're using, and then solve for what you need. All right, next one, Avogadro's law. We've already run into Avogadro. He's, Avogadro's number for the moles, so we're talking about moles. So it says the number of moles in volume, and this one's just pure common sense. The more gas you have, it takes up more space. So if you have more moles, you have more volume. Hey, that's pretty logical. Once again, the equation works the exact same way. You're going to be given a question that's going to give you some moles and some volumes. You pick this equation, you plug in the variables in the right spots, and solve for the one that's missing. All right, next one's a little bit different. This is Dalton's laws of partial pressure, and this is John Dalton, the one who did the atomic theory of matter. Same guy. All right, so in a mixture of gases, like air is a mixture of gases. It's got nitrogen, oxygen, water vapor, carbon dioxide, argon, and other things. Each component can be said to exert part of a total pressure, and this is called the partial pressure. So if nitrogen is 70% of your mixture, then you would say that 70% of the pressure is due to the nitrogen. Okay, and that is its part. And then we can take all of these partial pressures and we can add them up to get the total pressure. Okay, so this is the equation. The partial pressure of A is the total pressure times the mole fraction of A. So like I said, so if nitrogen is, in terms of moles, is 70% of the air, then we would do total pressure times 0.7 to give me the partial pressure due to nitrogen. And then we would say oxygen is 27%. And so we would do 0.27 times the total pressure, give you the partial pressure of oxygen. We're not going to use it in this course, but in a college course or an AP course, we can use partial pressure to basically be our unit of concentration within mixtures of gases. Okay. So, like I said, so it's one way of talking about it, and it's often used in calculations. All right, ideal gas law. Ideal gas law basically takes all of the other gas laws, with the exception of Dalton's, and pushes them into one equation. But in this case, we're not looking at how a system changes, we're just trying to find a missing variable. And so ideal gas law is PV equals nRT. And so you can kind of see where we've got pressure and volume are on the same side. But like in Charles' law, volume and temperature were on opposite sides. And so they're on opposite sides here. Same thing with Avogadro's law, moles and volume. They're going to be on opposite sides. And this R thing is called the gas constant. And the gas constant has so many different values depending upon what unit you're using that this will always be given to you because it's going to vary. So for example, if I'm using pascals and meters cubed in Kelvin, I get this one. If I'm using millimeters of mercury in liters, I get this one. And if I'm using meters cubed in atmospheres, I get this one. And so it all depends on what you're talking about, what unit you're using, that will determine your value of R. And so that is important to keep track of. So the ideal gas law, as the name implies, assumes that gases are ideal. What this means no intermolecular forces, that basically that they're acting as perfectly like a gas as possible. So for a lot of gases, this works fairly well. Happens to be that water vapor at room temperature and normal pressure is not ideal. But for calculations in this class, we're going to stick with ideal. If you want to get into non-ideal situations, you can go be a chemical engineer and learn all about the crazy ways they account for things not being ideal. All right, so let's look at how this looks as an example. What will the volume of 13.25 moles of argon be at 98,000 pascals and 21 degrees C? The easiest way to spot that a question is an ideal gas law question is, first of all, it gives you three different variables: moles, pressure, temperature, and then it's asking for volume. The other key thing that's kind of a big clue here is there's no change. We're not changing moles, we're not changing pressure, we're not changing temperature, we're not changing the volume. And that means we're using the ideal gas law. So moles, pressure, temperature, those are my variables that I'm given. Once again, take that temperature and convert it to Kelvin by adding 273. Figure out what equation I'm using. Like I said, I'm using this one because I've got three different variables and I've got no change. There's nothing's being changed. So this is the equation I need to use. Plug in your variables. This is the correct R value from the previous page. And you get that the volume is 0.33 meters cubed. And so that's using gas laws. So like I said, I give my students a sheet of paper with all the gas laws on it. And so I'd encourage you to keep the gas laws where you can see them. And then I give them values of R. And basically it's just a matter of looking at the equation, figure out what variables you have present, If you're given pressure and volume, and that's all you're given, that's Boyle's law, P1 V1 equals P2 V2. If they give you moles and volume, that's Avogadro's law. If they give you temperature and pressure, that's Gay-Lussac's. And so you need to know which law goes with which. So identify your variables, figure out which equation you need to use, and then plug it in and solve with a little bit of algebra. And so that's gas laws. It's very much just a problem-solving word problem type chapter. So with that, we'll see you in the next unit on solutions and equilibrium.